All right. So in the last video, we talked a little bit about 7.1 and finished it off. And this worksheet is going to go through a couple of really interesting ways we can use the information that we learned from 7.5. So we'll go ahead and jump right in. Now to find this, of course, you can go over to the College Trigonometry OneNote and go under Reviews and Worksheets, and it is page 7.5 worksheet. All right, let's get started. So we'll consider the point 3, -4 on the terminal side of some angle theta on the circle x squared plus y squared equals r squared. Now you should remember from algebra that this gives you just our standard circle. Well, it's a pretty bad circle, but yes, it's a standard circle with some radius r. And the point in question is 3, -4. So we're going to move over, let's do 1, 2, 3 in the x direction, and then in the negative y direction, 1, 2, 3, 4. So that's, call it about right here. So this is our angle theta. So sine theta, in this case, we know that sine is opposite over hypotenuse. So this is going to be, let's label these sides so we remember this side is -4 and this side is 3. Actually, I can just redraw this triangle real quick like this to make our life a little bit easy. So it's -4 and then 3 here on bottom. So we have -4 over the hypotenuse, but we actually don't have the hypotenuse yet. So let's go ahead and solve for the hypotenuse. So doing this, we have we'll use our Pythagorean theorem. C squared equals a squared plus b squared. Therefore, c is equal to the square root of a squared plus b squared. In this case, it's equal to the square root of 3 squared plus 4 squared, -4 squared. And this turns out to be the square root of 25, which is 5. So that means that our radius in this case is 5. So we now have, we can take this hypotenuse and write it as 5. Cosine is the adjacent, so 3 over 5. Tangent is the opposite over the adjacent, so -4 over 3. Cosecant is 1 over sine, so -5/4. Secant is 1 over cosine, so 5/3. Cotangent is 1 over tangent, so -4/3. Oh, excuse me, -3/4. Now, if you remember, the title of chapter 5 is the unit circle, right? So we're beginning to build this unit circle. We already talked about what happens if the radius is 1, and we can build our our functions based on that. But now there are actually a couple of really special triangles. Now we've already encountered these triangles before, but it wasn't really obvious how we were going to make that work for a unit circle. Now the thing is, if this triangle right here, this first one here in blue, the radius is going to be, if we were to superimpose this on a circle, well, that wouldn't be unit circle, would it? Because this would have a radius, right? If this were the point that were on the edge of the circle, then that would give you a radius of √2, which is not the unit circle. So what we're going to do is we're going to divide everything by √2. And this gives us 1 over square root 2. Actually, I'll write this right here. This side is 1 over square root 2, and then the radius now becomes 1. Now this is something we can work with because now we have it in the form of our unit circle. So we can ask, well, what is sine of 45? So in this case, it could either be this angle or this angle, and this is really important. So sine of 45, sine is the opposite over the hypotenuse. So this is 1 over square root 2, and then divided by 1, but I'm not going to put that. And then we have cosine of 45. So that is the adjacent, 1 over square root of 2 divided by the hypotenuse, which is 1. So Again, I won't write that. So this is an instance in which the sine and cosine are the same. Now you should expect that, right? Because if these, you may remember from high school geometry, I don't remember the exact name of the theorem, but basically, you know, these sides, these opposite sides are going to be the same specifically because their angles are going to be the same, right? So that's something that, you know, you may remember, but if not, that's fine, because this shows how this ends up being, you know, this is a different way to derive the same basic idea. So now we have a similar situation where we want to put this triangle, we want to put this point on the edge of a circle. Problem is that we have this 2 right here as the radius, and that's not going to work for a unit circle, so we need to get rid of that. So we're going to divide everything by 2. So this becomes square root of 3 over 2, and this becomes 1/2. So now we can ask, what is sine of 30? Well, that's 1/2 divided by 1. Oh, excuse me, this is 1 because we divided everything by 2. So I'm not going to write that, so sine of 30 is just 1/2. How about cosine of 30? Well, cosine of 30 is the adjacent, so root 3 over 2 divided by the hypotenuse, which is 1. So we just have root 3 over 2. So now we can see that we have our standard unit circle, right? The fact that we have these points right here, 1, 0, 0, 1, you know, negative 1, 0. This lets me know that, you know, I've got my radius, excuse me, got my radius right along here, and I'm going to start off, and it's laying on the x-axis like we do normally. Now remember that with the triangles we had before, they weren't in unit circle form, so to speak, because the unit circle has a radius of 1, and that's why we had to divide out and get those radiuses, which was the hypotenuse, to be 1. So, and this is why this is important, because we can play around with a couple of angles that we can know exactly. So the first one is to draw it with a theta of 30 degrees in standard position. So we're going to draw our theta of 30 degrees. I'm going to zoom in here a little bit. 30 degrees, and then we're going to do the same thing here. It should be a little bit bigger. And this is going to be 60 degrees. Now the question is, do we know what these 2 points are? Well, we do, because up here we determined that sine of 30 is 1/2, and sine, remember, is associated with the y coordinate. So this idea is that this piece right here, I'm going to do this in green, this piece, whatever it is, has length sine of 30, which we know is 1/2. And this length down here, I'm going to do this in blue, is the cosine of 30, which we know has a length of square root of 3 over 2. Now that means that we can create this point of, well, we had to move over square root of 3 over 2, and we had to move up 1/2. So we actually know what this point is on the unit circle. Similarly with this one, we know that for 60 degrees, we can we'll kind of look at this triangle from the other direction, right? Assume that the 60 degrees is, how do I want to write this? I'm going to write this like this, yeah. So we'll go ahead and draw it like this. So we've got a 60 degrees here. So this tells us that this side is 1/2, and the side opposite 60 is root 3 over 2, and then this side is 30, here 1. So in this case, it doesn't actually ask us to do it, but I'll go ahead and do it right now. We can do sine of 60 and cosine of 60. Sine of 60 is going to be root 3 over 2 over 1, right? But I'm not going to put that. And then cosine of 60, well, it's the adjacent, so it's 1/2 over 1. I'm not going to put that. So we just get 1/2. So we know what this point is, right? I had to go over, I had to move in this direction right here. I'll do this in blue. I had to move over 1/2, and then I had to move up root 3 over 2, which tells me that this point is 1/2 root 3 over 2. So these 2 points where we have 30 and 60, we know exactly. Draw right here again, root 3 over 2, 1/2, 1/2 root 3 over 2. All right, so how about for 45? This is going to be a pretty similar situation. I'm going to draw 45 degrees here. So the question is, how far do I have to move to get to that point that is sitting on the circle? Well, we remember from above that the cosine, which we associate with the x-axis, was, let's see, what was it? It should be 1 over square root of 2, correct? Yep, 1 over square root of 2. So 1 over square root of 2. And the sine actually ends up being the same. We have to move up 1 over square root of 2. That means that this point is 1 over square root of 2, 1 over square root of 2. So I now actually have 3 points that I know where they are, right? I know if it is 60 degrees, and I know if it is 30 degrees. And then we have 45 right here. So actually I'm going to put that on a different one, but just to show that we have now 3 points that we can play with. And it turns out we can actually, we'll see what happens. We can do these as negatives and we can keep going. And these 3 points right here are actually going to allow us to fill in the rest of this, the rest of the unit circle. So now we're going to use the same approach for if theta is 120. So if this right here is 90, so I'm going to go 90 and then another 30 degrees. So I've gone 90 and then I've gone an extra 30. So this angle right here is an extra 30 degrees. Now, can we figure out this point? Well, yes, we can. We'll go back up here and remember, actually what I want to do is take, so we know the side opposite of 30 is, I'm going to blow this up a little bit. The side opposite of 30, we remember, is going to be 1/2. And this angle is 60. And the side that is opposite 60 is going to be root 3 over 2. So what is this point? Well, in this case, we had to actually move in the x direction negatively, right? If this is, anything on this side is negative, well, for the x, that means that this point is going to be negative 1/2, and then we had to move up root 3 over 2. So we know what this point is exactly. Let's try this with 240. So if we go all the way, this right here is 180 degrees, and then to get to 240, we need to go another 60. So we'll call this angle 60. That means that this one is 30. So we remember that the angle across from 30 is 1/2, or excuse me, the side across from the 30-degree angle is 1/2, and the side across from the 60 is root 3 over 2. And this means that this point right here is, well, we have to go negative, right, in the negative direction because everything on this side of the y-axis is negative, so this is negative 1/2. But we now had to go down, so everything that is below the x-axis like that is in the negative y region. So that means this root 3 over 2 is negative root 3 over 2. Just make sure that's blue so that we know what we're doing. Fantastic. So in this way, even though you might be thinking, oh, well, how do I solve for like, 240 or, 300 or something like that? Well, you don't, and that's okay. Because you recognize that, well, you just move to the quadrant that you're looking at, right? You move 180 to the third quadrant, and from there you can build your various triangles with the side lengths that you already know that we computed above. Now, for the sake of making sure that this looks nice and that this isn't confusing if you look at why are these numbers different, I'm going to go ahead, now that we know that these need to be negative, and make that negative, and then this negative 3/2, or root 3 over 2 is negative as well. So that way it all, what's on here is also what is in the points. So let's try another one, 315. So 315, well, what do we know that looks kind of like 315? Well, I know that if I go 180 and then 90, this gives me 270. Actually, I think I'm gonna write this out here. So I've gone 270, and then 270 plus 45, this angle right here is gonna be 45, will give me 315. So I remember 45, both sides that are opposite the 45-degree angle, I can go ahead and label this as 45. Both sides, in this case, in the x direction is 1/2, 1 over square root 2. And in the y direction, it's 1 over square root of 2 as well. But now we have to stop and check. I moved to the right, in the positive direction for 1 over square root of 2. I moved to the right in the positive direction for the x, so that means that x is going to be positive 1 over root 2. But then I had to move down in the negative y direction for the y portion of it, which means that this is negative 1 over square root 2. All right. Now, I want to take a quick second to say that there is an equivalency. So the square root of 2 over 2 is equivalent to 1 over the square root of 2. So sometimes you may see it written like this, but they're the exact same. So, if you're wondering, oh, hey, on this it told me that it was, root 2 over 2, is that a problem? The answer is no. These are the exact same. And you can actually do this. I'll actually show you how to do this real quick. So if you have 1 over square root of 2, you'll multiply it by square root of 2 times square root of 2. Now remember, you can do this because square root of 2 over square root of 2 is just 1, right? You haven't actually done anything. So up top, you get square root of 2, and on bottom, you have square root 2 times square root 2, which gives you just 2. So that's how these two can be transformed into each other. All right. So now we're going to use periodic properties to find the exact values of the trigonometric functions. So the idea is that we can take a value, a radians or degrees or something like that, that looks kind of weird. It's not one that we recognize, but then rewrite it as some angle plus its period. And then once we do that, we can actually disregard the period because we know that all we've done is just go back to where we started. So for example, with secant of 7/3 pi, we can recognize that 7/3 pi is equal to 6/3 pi plus 1/3 pi. But hey, this 6/3 turns out to be just 2 pi. So what that means is that because that's the period, right? We have this period right here. This means that secant of 7 pi over 3 is exactly equivalent to secant of 1/3 pi, or pi over 3 is how it's more often written. So the question is, how do we determine what secant of pi over 3 is? Well, so do we remember pi over 3 is 60 degrees. So I'm going to make myself a nice little unit triangle with radius 1. Now, there's a big circle that this is a part of, but I'm not going to draw that right now. But that's where this is coming from. And so I've got 60 degrees here. Now, if this is 60, this is 30. I know that the side opposite 60 is root 3 over 2, and the side opposite 30 is 1/2. All right, fantastic. So secant is 1 over cosine of pi over 3. Now, do we remember what cosine of pi over 3 is? I'm going to rewrite this as 1 over cosine because we're using 60 of 60 degrees. So cosine of 60 degrees is, well, it's the adjacent over the hypotenuse, so 1/2 over 1. But now we're going to flip it, right, because it's 1 over cosine of 60. So this actually ends up being equal to 2. So that's how we would find something like that. Now, this is a multi-step problem. First, we had to recognize that because of the periodicity of secant, we could rewrite 7 pi over 3 as 6 pi over 3 plus 1/3 pi, but 6 pi over 3 is just 2 pi, so we can actually just get rid of it. So we're going to rewrite secant of pi over 3 as 1 over cosine of pi over 3. And if you wanted to just skip this 60-degree step, that's fine. If you just remembered, oh, pi over 3, that's associated with root 3 over 2 and 1/2, that's fine. But I converted it to 60 degrees and drew my little triangle, solved for cosine of 60, and then just flipped it. So how about tangent of pi? Well, tangent of pi, let's see if we can remember. This is 0 and 2 pi, and this is pi over 2, and this is pi. All right, fantastic. So with pi, the radius is sitting, this hypotenuse is sitting, which is the radius, is sitting directly on the x-axis. So we had to move -1 in the x-axis and 0 in the y-axis. So this means that tangent is sine over cosine, right? Opposite over hypotenuse. The opposite is 0. So this means that tangent of pi is just 0. I could just as easily have asked, what is tangent of 10 pi? Right? What would that mean? That would mean that I go 1 pi, 2 pi, 3, 4, 5, 6, 7, 8, 9, 10. Now I've landed back here. Okay, so I'm right here. What is this? Well, in this case, I go over in the x direction positively 1 and go up 0. So this is sine, tangent is sine over cosine. And so in this case, sine is 0 over 1, and this is just 0. All right. How about sine of 495? So let's think about, can we make sine of 495 as this 495 degree as 360 plus something? So 495 is equal to 360 plus 135. So this 360, of course, is our 2 pi, so we can actually just disregard it, right? It's a period, so we're just back to where we started. But now we have this 135. So let's think about where 135 takes us. I'm going to draw our little unit circle. So I'm going to go 90, and then after I go 90, I'm now in this quadrant right here, quadrant 2, and I have to go another 45. So if I had my little circle right here, this would mean that I have, 45 right here. Actually, those will end up being the exact same. Yeah, actually, I could draw it either way, but we're more used to drawing it a little bit like this, so I'm going to make sure to keep it that way. All right, so I've gone 45 extra to get me to 135. This side over here is 45 degrees. Now we remember that the sides opposite of 45 degree are 1 over square root of 2, right? This side is opposite of this 45, and then this one over here is 1 over square root of 2. So sine of 495 actually turns out to be sine of 135. Now, of course, these are the links, but now I have to take into account the fact that we're in the negative quadrant, so I had to move to the left, right, of the y-axis and the x direction, which means that this is now negative. But that's okay because we're just looking for sine, and remember, sine is associated with the y direction, so this sine should be 1 over square root of 2 because we've moved in the, right, if you imagine this point right here, this point is going to be negative 1 over square root of 2 and then 1 over square root of 2. All right, so we're nearing the end. So we can use even and odd properties to find the exact values of things that we don't really know. So let's start off with cosine of negative 45. So negative 45 is not something that we normally think of having memorized, but that's okay because we can look here and see, oh, hey, cosine is actually even, right? So this means that I can rewrite this as cosine of 45 degrees. And we remember that 45 is one of our special triangles that we've been, or one of our special angles that we build our triangle from. So I know that this is 1 over square root of 2. So sine of negative pi. So sine is actually odd. So I can write this as negative sine of pi. Now sine of pi, let's remember real quick, we've got our thing. So this is 0 and 2 pi. This is pi over 2, and this is pi, and then this one down here is 3 pi over 2. So if my radius is sitting directly along the x-axis, I've gone -1 in the x-axis and 0 in the y-axis, so this actually is just 0. Now, this makes sense, right? Because if I were to start in our normal position where our radius is sitting against the x-axis and I go over pi, I end up exactly like this, right? Leaning up against the negative side of the x-axis. But that would be in the positive direction, so this is in the positive direction. I can also, of course, go in the negative direction, right? So I'm gonna go this direction, this is negative. Now this would be moving negative pi, and of course I end up at the exact same place, just hanging out right here on the negative side of the x-axis. So, you know, you can think about this in even odd, but of course, you can also just think about this in terms of, okay, what happens if I take this radius and whirl it around the center? All right, so how about tangent of -13 pi over 4? So tangent over here is odd, so this means that this is equal to negative tangent of 13 pi over 4. All right, but we don't know 13 pi over 4, do we? But what if I wrote 13 pi over 4 as, let's see, what do I want to write it as? What if I wrote it as 12 pi over 4 plus 1 pi over 4? All right, this looks like we're getting somewhere. All right, but 12 pi over 4 is just equal to 3 pi, and then we have 1 pi over 4. So what this looks like is I start over here and I go 1 pi, 2 pi, 3 pi, so I'm essentially going to start right here, and I'm going to go an extra pi over 4. Now pi over 4 is the 45-degree angle, so this angle right here is pi over 4, or 45 degrees. So this is my angle theta. And if we remember tangent of pi over 4, do we remember what that is? Let's see if, did we do it up here? Well, we didn't, but that's okay because we have this 45 degrees, and so 45 degrees is pi over 4, and that is sine over cosine, which is just 1. So this means that tangent of pi over 4 is just 1. Oh, sorry, I went too far. So we'll write this side as 1 over square root of 2, and we'll write this side as 1 over square root of 2. So tangent of 13 pi over 4 is just 1, but then of course it's negative of that because it's an odd function, so we get -1. All right. So that is the end of this worksheet. Down here we have the domain and the range, which we went over a bit in class and then I finished up on the other video. So, you know, in class we kind of just, and in the last video, we just went over the more theoretical foundations of how to create the unit circle. And what this worksheet did is it started off with the construction. We already built these two triangles before, right? But when you have this radius right here and then you divide out the radius, you actually end up getting two triangles that allow you to understand and, well, memorize, although you don't have to, of course, but memorize or to understand very specific angles on the unit circle. Now then, using our periodicity and our even and odd properties of the trig functions, we can actually fill out large parts of this unit circle without having to resort to a calculator or something like that. And we can also find all kinds of really interesting angles that wouldn't be obvious to us. It's not obvious how 495 degrees can be solved, but we recognize it as 360 plus 135 and the periodicity of sine or cosine or tangent or whatever, right? And now we can do something with that. So that is the idea behind this worksheet. And so I hope that y'all watch this and work through this yourselves. And if you have any questions like that, we'll talk about it on Monday.